All right, line N1, this is going to be learning task B, where we're just going to describe the layouts of the systems that we are going to be looking at. Basically, block diagrams over here. They're simplified block diagrams. They're what we refer to as one-line diagrams. They're just showing the interconnection from component to component without showing the individual components, where this one is tied physically, the line 1 wire and the neutral wire and the bond wire and things like that. We're just looking at this as a broad overview. We'll start with the standalone wind power system over here. Standalone wind power systems are going to be commonly used for remote little sections. We'll use them for wells in a lot of cases because we can have an electric pump down, a deep shaft well pump. Doesn't require to have priming or anything like that. If you've got a surface-mounted wind pump, you do have to go and have this thing kept at prime. And if that dries out, it causes problems. But we commonly will see these ones used for, small scale, just single type of load that we are going to go and have. This case over here, they're showing that we have got a wind turbine. It is going to be generating wild AC inside of here because we are not going to be regulating the speed that's going to be off of that or the voltage. The faster the wind blows, the higher the frequency and voltage, the slower, the lower. Both of those are going to be. We need to go through a disconnect. From the disconnect, we are then going to go down to a load controller. The load controller is going to just go and act like a three-way switch inside of here. We'll describe it on this one. Other ones we won't need it anymore. But it's going to act as a three-way switch, and it is going to be able to go and send some of it over to the AC load. It's just going to monitor to make sure that we don't go too much to the AC load, that we're going to burn our pump out. Anytime that we've got really, really fast winds, what we're going to do is we're also going to go and turn on our diversion load. It actually acts less like a three-pole switch, more like it's an array of switches. So it's normally going to be driving stuff out to my AC load. If things get out of control, it can open that switch like that. But it is also going to be able to close in this switch over here or open this switch based on whether or not it needs to divert that. So we'll just burn it off as extra heat inside of these. You do need to go and have a AC disconnect for these ones. And your load could be, pumps. It could be anything like that. It could also go and be an AC load that would be a charge controller, where I'm going to go and rectify this, the AC that comes in, I'll convert it to DC and then pass that into batteries, etc. That's going to be something more like this, which would be an off-grid wind power system that we would have. We're once again going to be generating wild AC. Varying, based upon the wind speed, but what we're going to do is we're going to go and rectify it. So we're going to convert it into DC. So right over here, we're going to go AC. Well, it's actually inside of this device over here. So we'll go AC. We're then going to go and convert that to DC. Our DC is going to go and have a disconnect. That DC is then going to go into a charge regulator. That charge regulator is going to say how much can I send safely on to the rest of the system versus how much do I have to burn off as heat because we're going too fast. So it's monitoring that. Whatever it can safely send goes through a DC disconnect, and then it is going to go and be used to charge my batteries. And it is also then going to get fed out of here down into my inverter. My inverter is then going to change this thing from DC back into AC. And then my AC goes through an AC disconnect, goes into my service disconnect, which is going to be like my panel, and then out to my actual loads itself. If I lose, whatever is providing the renewable energy, so let's say we have got no wind that is happening right now, so we'll scratch that over there. That would mean that we're not generating AC, which means that we're not converting anything to DC, right? Zero AC results in zero DC, which means that I don't have to worry about, any of this section over here. And then inside of this DC disconnect, my battery, which was being charged before, is now going to go and reverse flow and is now going to go and flow back through my inverter over here and then continue to generate that AC for me. What we have is when we lose our renewable, basically everything upstream from here is going to be dead. And we're at that point going to just be feeding through here. There's going to be a power blocking device on this DC over here that is going to prevent us from back feeding up and through there. Grid tie is going to be a little bit different. Once again, grid tie is going to need us to go and read what we have coming from BC Hydro. So we are going to go and have a service box. This is going to be a service box that is going to go and be fed by BC Hydro. So we've got BC Hydro itself coming in to my service box. That service box is going to have a connection to my system AC disconnect. So this is just a switch going through here. And that system is going to go all the way up here to that inverter. So we can read what I'm getting for my BC hydro volts and frequency coming in from there. On this end over here, I'm going to be generating, once again, we're going to go wild AC off of this thing. The wild AC, because it's, unruly, we're going to go and rectify it, put it into DC. So then it goes into DC. That DC passes through just a disconnecting switch into my inverter, and then in my inverter, that DC is then going to be converted back into AC that we can then feed back into our service box. So this green line over here, what I want you to note on the green line is that this is just going to be voltage that we are sensing. We're not taking anything, we're just reading what the voltage of the frequency is and we're matching up to it. This inverter is designed to go and match to that. We feed AC power, AC current, into our service box. From our service box, we're going to go to our actual loads out of that thing. Now, I can be feeding my loads through this pathway here with the red line over here, which is what I'm generating. I can feed through to my actual loads like that. If I don't have renewable, let's say it's, the wind has shut down, or if I was using photovoltaics, that there was nothing over there, what we would then be able to do is we would be able to feed it in from the hydro side over here. So I can go and only use hydro when I'm actually looking for it. On some of them, we can actually backfeed to the grid as well. So if I'm generating, I got a lot of wind right now, and I'm generating more AC than what I need, some of the rest of that will go back out over here as well. And what BC Hydro does is they just kind of use these the same way that we do like bars. They just cancel them out on your bill. The amount of power you're taking in versus the amount of power that you are going to be taking out that we will have over there. This one over here on the bottom also is going to be generating wild AC. The wild AC is always inside of the alternator. This one over here, when we rectify it, we pass it out as regulated DC at that point. This one, we're going to pass out the wild ACs to our AC disconnect, and then we're going to do the rectifier on the outside. Basically, this whole section is this whole section. From there, we don't see a lot of differences other than that this section over here doesn't have a DC disconnect. Part of my rectifier. It could be external though. We could have another DC disconnect in line with that. For the rest, operates the same way. When I have got renewables, I'm going to be able to feed those into my inverter, which I can then feed out as AC to my loads out of the service box. When I don't have renewables, I would be able to go and take in power from BC Hydro. And when I've got too much renewables, more than what I need, I can feed those back out as well as to my loads themselves. There are other variations as well. There's another one that's the Dfig, doubly fed induction generator. These are very common in large power systems. That allows me to go and synchronize the generator at the genset without having to be electronically with the utility grid. It's basically going to slow the roll on the rotor itself. So I'm going to go and feed back in, once again, from my supply authority on the Dfig. The Dfig is going to go and provide a voltage signal that is going to be run to the actual windings of these things. And so I'm going to go and synchronize with that one over there. Note how it says it's doubly fed. The doubly fed refers to the fact that there's going to be multiple sets of windings. One of the sets of windings is going to be fed by the supply authority. The other winding is going to be fed by the induction generator, what I'm actually generating off of that thing. All of this is going to be housed inside of the nacelle. You will not go and find these things as being standalone systems. They're very heavily engineered. You can't just kit bash one of these together with a whole pile of stuff. So your Dfig, you feed in from the supply authority. You're also going to be generating then off of your wind speed over here, and then that is going to go and be sent back out as AC that we are going to go and have. That AC gets fed through this pathway back as AC into my service box, where once again I can either go to my loads or I can feed it back onto the grid if I have enough for what I need. That's wind. Solars are done through, multiple arrays, where we are going to go and have photovoltaic modules. So my individual, what we refer to as solar panels, that's going to be these ones. Those are going to be put into what we refer to as a combiner box. The combiner box is going to go and take all of those individual components. This is for a little standalone direct-to-load photovoltaic. So, I'm running something like just a pump or something like that off of this thing. I'm going to go and take all of that combined voltage and current. It's not frequency because it's DC. I run that into a load controller or maximum power point. This is going to be tracking. It's going to be adjusting my panel so we get maximum amount out of it. And then I just run that out to a DC load. You'll note that there's nothing AC whatsoever. We're just taking DC and running it directly out as DC. It's like a little DC pump or something like that. Standalone photovoltaic systems, going to be a little bit more complex. These are going to go and usually require a battery because, as you know, the sun is not out at night. It goes to bed. So, since the sun is going to bed, we need to have something so that we can stay up later. Once again, we're going to go and have DC sections. So this is going to be DC. I'm going to go and combine that DC with other DC from other modules. We've got many modules together. That is then going to go into a DC disconnect. There's a lot of rules inside of my code book about these disconnects because there's been a lot of like first responder, fire rescue services. A lot of their personnel have been injured by these in the past because they go and they ventilate. I don't know if you've ever, if you know anybody who works for the fire service. Usually you do. That's like one of the first things they tell you about. Hey, you work for the fire department. But anyways, what they'll do is they like to go and ventilate. Ventilate basically is, destruction with an axe that they're allowed to go and do. As soon as there's a fire, they're like, we got to ventilate. So they bash the windows in with a axe. And there is, reason that they got to do it. But oftentimes they will also chop holes in roofs with chainsaws and with axes so that they can go and control the flow of, smoke and heat and stuff like that. It helps them with the fire. What happens is if we got a bunch of these on this roof, all of these are going to be generated. The sun is still out, possibly, when this building is on fire, and those systems have not burnt, so we need to go and have a way that they can rapidly shut them down. There's a pile of rules about rapid shutdowns inside of your code that are there to save life. They talk about, that we need to have these systems identified so that they don't just start chopping holes in the roof and chop through hot cables that we're feeding down through there. Those DC are going to be fed into a charge regulator. That charge regulator is just going to vary the amount of DC that I'm going to go and drive through there. It's not like where we have to go and have a diversion load. Diversion loads, we need those with wind-powered systems. We don't need to have diversion loads with photovoltaics. We just shut them off if we don't actually need them. So my charge regulator is going to go and, open the valve basically or close the valve. It's going to be a semiconductor that we're going to have. It is going to go and send DC through the DC disconnect where it's going to be able to be picked up by my battery. We can charge the battery. And then I'm going to go and from there also feed on down to my DC distribution and to my loads itself. When the sun goes to bed, all of that shuts down over there. And then we would start to pull out of my batteries, feed that back to that DC disconnect to that DC distribution. Once again, we're going to go and have one-way valves, diodes that we have talked about in electronics before, that are going to go and prevent us from backfeeding out of that system, but that are going to allow us to, have fed into that system. If we want to go to AC, an AC one is identical other than we're adding in over here. We went DC distribution out of the DC disconnect. Now, instead of going into DC distribution, we're replacing that with an inverter and feeding everything downstream with AC. So the rest, we take the DC, we combine it, we have a disconnect, we have a charge regulator that limits how much goes through there. We go through into our batteries, and then our batteries are going to be charged off of this thing continuously, as well as we're going to be feeding our DC in there, and we're going to be feeding DC into our batteries. That's all happening while we have got sunlight on the modules themselves. That DC that goes into here then gets converted into AC. The AC goes through a disconnect, goes into my panel, and out to my actual loads itself. When the sunlight goes out, we are then going to go and reverse the flow from the batteries back up and in, so we continue to feed the DC into here and continue to generate that AC that we will have off of it. By the way, for first responders, they do have blankets that are going to be, they're fairly thin blankets, but they're going to be completely opaque, and they'll put them over top of photovoltaics. If they don't know what's going on, guaranteed way to shut off the PVs, stick a blanket over top of it. If you ever work in photovoltaics, you buy yourself some good tarps so that you're going to be able to go and cover over stuff, a tarp and a bit of duct tape, and you can make sure that a system is going to be shut off while you are working on it. Don't get a see-through tarp, don't get one of those light blue ones that the light passes through. You want to go and get one of those heavy black tarps or the silvered ones. Utility interactive is also going to be available. That's going to be a grid-tied one where I'm going to go and have my volts and current that I can go and feed back and forth from one side to the other. Once again, photovoltaics receive light. That light gets converted into DC. We combine that DC into a combiner box over here, and then we feed out from there into my disconnect. And then that's going to go and tie into a grid tie inverter. What that grid tie inverter is doing is it is always monitoring what I have got over here from BC Hydro. So BC Hydro feeds in, and I'm just going to go and monitor the voltage over here at the grid tie inverter. I'm going to watch that, and I'm going to go and take my DC and I'm going to synchronize it to that as I convert it into AC. And then I pass that AC current out to my service disconnect. From there, it goes down to the loads. They don't show the loads off of these ones over here, but it's going to go and pass through to my loads that I'm going to have. And if I've got any extra, I can sell it back to BC Hydro, and it's because the synchronized can go back out onto that grid. These ones don't have energy storage because they use the grid as storage itself. And I know that sounds really weird because you're like, but the grid is active, you know, it's not passive. Where is it storing the power? What it is it's storing a credit for you. So whenever I've got extra DC that is going and being generated, tied in, converted as AC, and I send that back out over there, I'm going to go and receive a credit on my hydro over here. And then when the light turns off and I no longer am generating that DC over there, what I'm then going to be able to do is I'm going to go and be able to cash that credit in. And I'm going to be able to go and drive this thing back to it. So we call it using the grid as storage. This is going to be what we refer to as distributed photovoltaics, what we talked about at the very beginning of the last video, where these massive companies go and, you know, get grids on people's houses, and they say, look, you don't need to have any battery or any storage like that. None of these systems, well, I shouldn't say none, but a lot of these systems don't have batteries. The batteries are usually there as a, like, you know, extra option you can pay for. Like, oh yeah, and if you want to have, you know, backup power, you can pay for a battery system that you are then going to go and tie onto this thing in case the grid itself goes down, because the grid still can go down. You're using the grid as your storage so that you can have something at night, but if the grid goes down, you don't get, you don't get the option to go and cash that in. So these ones will just be big boxes that you will see. And usually it's going to be all of my photovoltaics come from the combiner down to that. I'm going to go and have a meter that's going to be on this side, and I'm going to feed right into there, and then out of there is going to be a load. And it's going to contain all of this stuff on the inside of them. Smaller ones that I'm going to go and use will have microinverters. Microinverters are going to be on the roof itself. So I'm going to go and have the actual photovoltaic array that plugs directly into the microinverter. Note that I don't have a combiner box over here. What it is this micro array is just going to be synced up. So I'm going to go and have, once again, voltage. We're going to use this green line for my voltage that I'm going to be running up into here, and that voltage gets distributed to each one of these ones over here so that they know where the peaks are and what the frequency is. These are then going to go and take their DC that they're generating, so that's going to be the DC we're generating in here, and then they're going to go and synchronize it to what is on there, and they're going to go and send that out as AC current. Okay, so both of these are going to send that out as AC current. It's going to go through there to my service box, and from there it goes down to my actual loads off of these ones. As it goes down to the loads off of that one, if we have anything extra, we can go and send that out to the supply authority. These ones in some ways are a little bit more reliable than these ones, because these ones over here have got only a single large inverter that we're going to have. We're going to have to do the photovoltaic combinations. This one over here, we're just going to be taking AC lines back down and in. Big difference is between these two in the way that they look, what we see over here off of this one here. Let me just erase my earlier scribbles off of that one. This one is going to be a central inverter, so I'm going to go and take all of my DC, put it into a combiner box, and then tie it into this inverter. This one over here are going to be the micro inverters, where each one of these is reading what's on the panel, but then it's feeding it back out as well. It seems complex. The beauty of it is that it is complex, but we don't actually need to go and deal with the electronic complexity of it. We just hook these things up. Standalone hydropower. Standalone hydropower is going to go and run an alternator. Standalone hydropower is usually not going to be your term as being wild AC, because what we talked about before, you know, in the structure of the build of these things, the fact that we are going to go and have our intake, our canal, the forebay, and then we're going to have an overflow from the forebay to go and divert anything, that's going to allow us to maintain pressure. And as long as we got to maintain pressure, we know what it is because we can calculate the drop over here. We can go and calculate our frequency that we are going to go and have. So my speed stays the same because it's all based upon how far this water is falling down that mountainside over there. Through the penstock, obviously, we're not running this thing wild. We can go and generate as AC. We can also generate as DC. It really doesn't matter which one we are going to go and do. If it's going to be standalone hydropower, we're going to go and see my wild AC. Well, sorry, it's not wild AC, but my AC that I'm generated over here. We're going to run that through our disconnect into our load controller. And then we are going to be able to run that to our AC load, and we're also going to go and have a diversion load. Diversion loads are just in case there are irregularities. The overflow on the 4-bay gets plugged up, all of a sudden this thing would be running faster. We wouldn't have any place to burn that power off, so we need to have that diversion load. If I'm going to go and use battery backup, commonly done as well, we're going to go and do the same thing. We're going to have our hydro turbine. We're going to take the AC, we'll rectify that into DC. We might as well do it as close as we can so that we can, get this kind of over and done with and keep our efficiency up. We take that DC, we run the DC at that point. So here's AC, here is now DC. That DC goes through the disconnect into our charge regulator, which is going to go and say, yep, that's the amount we can pass through safely. No, that's too much. We'll burn that off over here. So that's going to be heat over there. Then pass into my DC disconnect, where it's going to go down to my battery, and it's also going to go and pass into my inverter, where once again it's going to convert to AC, and then it's just going to go through my distribution out to my loads itself. Once again, if for whatever reason I wanted to go and either pull more current than what this thing can go and run, or for whatever reason, I've got time of day or something like that for like high tidal power type of ones, and I'm not running off of them, then it would just reverse the battery flow. So the battery would now become the source and would feed that back into there. There are also places where this is useful if I'm going to go and have peak demands, where I'm going to be generally running enough. Let's go and take a look at that little house there again. That house could be normally just running, some lights and things like that. But every once in a while, you turn on the clothes dryer. The clothes dryer is a heavy amperage load, or you cook with all of the elements on your stove or something like that. When you do that, you're going to be pulling more current than this thing could necessarily generate. They're going to be limited, the amount of kilowatts. So let's say it's limited to, 5 kilowatts over here. That 5 kilowatts that I'm generating, if all of a sudden I'm pulling 6 kilowatts, I need to make that up from somewhere, so I'll make that up from the battery disconnect. So I would be pulling still from my hydropower, and I'd be pulling the additional kilowatt off of the battery and through there. Gridtie hydropower, probably the least commonly used of our renewables here in British Columbia. We are going to go and have to make sure that we maintain frequency once again. Usually these are going to be Dfig, doubly fed induction generators, same as what we talked about before on my wind power. And we are going to have to go and take signal in from the supply authority. So we are going to go and monitor that voltage. That voltage is going to be fed to one of my windings on the Dfig. The other winding is going to be my generation winding. We're going to go and take AC power off of that. That is going to be synced up from there. That AC current, we're going to feed that into our service box where it goes out to my loads downstream from there. And if I have got more than what I need, I can go and feed that back out onto the supply authority. Once again, if I would have to shut down my turbine, I don't know, you get a log or a stick or something like that that's been stuck inside of it, you would be able to, in the meantime, take your power back in from the supply authority. All right, that is our simple one lines of these. Know your components, how these things are going to be connected. Be very careful working around these things because you see so many components where we have got dual direction, stuff that is feeding in, feeding out, or being fed from two sides, AC and DC, and shutting off one side, whether that's going to be the photovoltaics or the generator, or shutting off, the supply authority. Doesn't necessarily kill everything inside of the system. These systems should have many warning labels on them. Once again, section 64 of your code is going to give you loads of requirements for labeling on these things for the sake of safety.